This video then is chapter 12, Differentiation, and if you're watching this as it comes out in 2019, the end of March, start of April, I'm just going to do videos for section 12.1 and 12.2 at the moment. In future years other things may follow, but I thought these would be helpful for my class this year. So, before we get into chapter 12, let's ask ourselves this question. What do we mean by a gradient? Well, we should be familiar with, if you've got a straight line, you can pick a point here on the straight line, you can pick a point here on the straight line, and we can call this the change in y, or the y change, and we can call this the change in x, or the x change, and a shorthand for that is delta y and delta x. This Greek letter delta, sometimes as a lowercase delta that looks like a D, sometimes as a capital delta that looks like a triangle. It's often used for change. So change in y divided by change in x is delta y divided by delta x, and that's what we mean by a gradient, by the steepness. The next thing we want to ask ourselves is, well, here's a curve. Does it make sense to say how steep is the curve at this point? And how steep is the curve at this point? And hopefully you're thinking, well, yeah, of course it does. The curve here is not very steep. The curve here is much steeper. This curve is getting steeper. That makes sense, but we've got a problem here because our mathematical definition of gradient is the change in y divided by the change in x. So if we're going to have a change, if we're going to have a gradient, we need a change in y and we need a change in x. But it makes sense to say, what's the gradient at this point? At a point, there isn't a change in y or a change in x. There isn't any change. It's just a single point. So what does it mean to say that at this point, the curve is steeper than at this point? The solution to that is that we're going to say, well, the gradient of the curve, by definition, is going to be the gradient of the tangent. So there's the tangent, here's a tangent, and this tangent has a steeper gradient than this tangent. And hopefully you can see that's going to work. When the curve's got a shallow gradient, the tangent's got a shallow gradient. When the curve's got a steep gradient, the tangent's got a steep gradient. So we've given meaning to this idea of having a gradient at a point. But it's important that we get in our heads that a gradient at a point is sort of an odd thing to think about, because a gradient is what's the change in y for every unit change in x? What's the change in y for every bit of changing in x? At a point, there can't be a change in y and a change in x. It's just a single point. But on the other hand, it has an intuitive sense, doesn't it? The steepness at a point, we understand what it means. I'm sure everybody's said that this point is not steep. The curve here is not as steep as the curve here. So it's something that we can see as a problem. Intuitively makes sense. Mathematically, we've got a workaround for the moment. And really, that's all that's going on in section 12.1. Is they're telling us that fact, the gradient at a curve is defined as the gradient of the tangent to the curve at that point. And then they're setting us an exercise that tests, drawing a gradient, drawing curves, and messing around with those sorts of things. I think really exercise 12a and section 12.1 is just to get us into the frame of mind of dealing with curves and functions and gradients and that sort of thing. And the maths in the chapter really starts at section 12.2. Okay, so section 12.2 goes something like this. If I've got a function, let's call it f of x. This is the function y equals f of x. And let's say we've got a y-axis and an x-axis, x-axis, y-axis. Okay. Now, if I want to find the gradient of the curve at this point, well, we've got a definition. It's the gradient of the tangent. But how do I find that? If I tell you the x-coordinate, you could take that x-coordinate and substitute it into f of x, and f of x would give me a y value. So the height of this curve at this point here is f of x, or if you like, the coordinates of this point are x, f of x. But I don't have an algebraic way of finding the gradient at this point. So the only thing I could do would be to draw a table of values, maybe get a computer to draw a table of values and get a nice curve, and then I'd have to draw a tangent on. And again, the only method that we've got at the moment, kind of pre-chapter 12, the only method that we've got for drawing the tangent would be to get a ruler and try and make it exact. And then we'd have to measure the tangent, measure the y change, measure the x change. And we've got two problems there. One is that it's a pain in the neck to do. It's going to take us ages. And the other problem we've got is that it's not going to give us an exact answer. It's not going to give us exactly the gradient of the tangent. It's going to give us the best guess we can get, the most accurate guess we can get for the gradient of the tangent. So of course what we want is an algebraic method which will always give us the gradient of the tangent. And this is how we're going to go about finding that. I'm going to pick another point on the curve because I know a method for finding a straight line if I know 2 points, right? I can do, we've seen it in a previous chapter in this book, is possibly chapter 5, I can't remember, but there's a chapter on coordinate geometry. If I tell you the coordinates are 2 points, we've got a way of finding, as a formula, the equation of the line between those 2 points. So I'm going to pick that point there, and I'm going to pick this point here a bit to the right on the curve. Well, what do I mean by a bit to the right? Well, I'm going to take x, and I'm going to add a bit to it. And we've just said a little while ago, we've got a notation for that. A change in x, we'll call it delta x. So this point here is this coordinate x plus a little bit delta x, okay? Now that delta x you should see as one symbol. That's not delta times x, that is delta x. That is a little change in the x value. So this point here is x, this point is x plus a little bit, okay? So if that is x plus delta x, the y coordinate of this point here is what I get if I put the x coordinate, x plus delta x, into f of x. So the y coordinate here is f of x plus delta x. In other words, this coordinate here has x coordinate x plus delta x, y coordinate f of x plus delta x. Okay, and that's this coordinate and that's this coordinate. Now, why have I done that? Well, I can find the equation of this straight line because I've got this set of coordinates and I've got this set of coordinates. They're not very nice, but I do have a method algebraically for finding the equation of this straight line, and specifically it's not really the equation I want, is it? It's the gradient I want. So the gradient of this straight line is f of x plus delta x minus f of x, that's the change in y, divided by x plus delta x minus x, that's so y coordinate minus y coordinate, x coordinate minus x coordinate. So we can simplify the denominator there slightly. So this is the expression which tells us the gradient of this straight line. And you might well be thinking, well, fine, we can find the gradient of this straight line, but we didn't want the gradient of this straight line. What we wanted was the gradient of the tangent. And I'll let's see if we can get this green to work. Oh, the green won't work. Let's see if we can get the black to work then. There we go. What I wanted was the gradient of this black line here, and I've got the gradient of this red line. So that's totally pointless having this one. We want this black one. Well, this is what we're going to do. Have you noticed that this delta x here is just a little amount x? I've not put a number in. I never said it had to be big or small. It's just a delta x. So what if I made it a little bit smaller? Instead of going from this point here to this point here, what if I went from this point here to this point here? Well, what I'd have then would be, let's see if we can get the next colour to work, there we go. What I'd have then would be this line, this blue line, okay? There. And then, so instead of this delta x here, my delta x would be the thing that would be this number here, okay? Instead of delta x being the gap from x to delta x plus delta x might just be this big. And what if delta x was a little bit smaller again? Let's go for a pencil. If it was a little bit smaller again, and this was delta x, then this line would be the one that I'd get. And hopefully you can see what's happening here is that we want the gradient of this black line, the gradient of the red line, the gradient of the blue line, the gradient of the pencil line. The lines are getting closer and closer and closer to the black line. So if I look at this thing, and I think about what happens as delta x gets smaller and smaller and smaller, I'm going to get something which is closer and closer and closer to the equation of this black line. So I could say, well, calculate this when delta x equals 1. That's a fairly small number. And then calculate this when delta x equals 1/2, and then calculate this when delta x equals, I don't know, an even smaller number, 1/10. Then calculate this when delta x equals 100th, and then calculate this when delta x equals 0.00001, and smaller and smaller and smaller, and hopefully you'll get a sequence of numbers, and that sequence of numbers will get closer and closer and closer to the gradient of this black line, and that's what we're trying to find. And the notation for that is the limit as delta x tends to 0 of this thing. Limit of delta x tends to 0 of that. Which is fine. Limit as delta x tends to 0. This means let delta x get smaller and smaller and smaller and smaller, closer and closer and closer to 0. Then this expression will get closer and closer and closer to something. And that something is the gradient of the black line. And often classes at this point, people that are following and paying attention and see what's going on, they say, well, fine, but why not just put delta x equal to 0? Well, look what happens when we put delta x equal to 0. First of all, the bottom of the fraction is 0. So we can't deal with that, right? We can't divide by 0. But even worse than that, look at the top. If delta x equals 0, then that delta x vanishes. So the top is f of x minus f of x. So it's 0 divided by 0. And that really creates a problem because 0 divided by anything should be 0. But anything divided by 0 is undefined. We can't do a division by 0. So we've got 0 divided by 0 and we've got a problem. What we can't do is 0 divided by 0, but what we can do is a very small number on the top divided by a very small number on the bottom. And if delta x is a very small number, f of x plus delta x minus f of x is a different very small number, and those two numbers get closer and closer to 0, and the answer for when you do the division between the two of them doesn't turn out to be 0, it turns out to be something or other, depending on what f of x is, okay? So the gradient of this black line is this, and the notation that we give that is this notation dy by dx, which you can see looks similar to delta y divided by delta x, okay? If we take delta y divided by delta x, that's the change in y, that's the change in x. And if we take the limit as the delta x gets closer and closer to 0, then that thing is called dy by dx instead of delta y divided by delta x. This notation is a bit confusing. It looks like a fraction. The reason it looks like a fraction is it becomes from this. But what we're really doing here is you're doing this d over dx, that's one symbol. And that means we're doing this thing called differentiation. That's the first time we use that word. Differentiation is the process of finding the gradient of the curve. And we're doing that to the curve, which we call y. So we're actually doing d by dx, we're doing this thing to y, okay? And it works in the same way as, you know, we've dealt with lots of things called f of x. F of x is a function. If you put a number in, it spits a number out, okay? So if f of x is the function x squared, I could put the number 2 in, it spits out the number 4. I can put the number 3 in, it spits out the number 9, and so on. Okay, you can put numbers in and it spits numbers out. This d by dx thing, you put a function in and it spits a function out. So I put in this function f of x and it spits out whatever this thing turns out to be in algebra. Okay, so it's not a fraction, something called dy divided by something called dx. It is take the function y and apply to it this process, work out the answer, and you will get an expression. And that expression will tell you the gradient of the function y at the x-coordinate x. Okay, what we're looking for is the gradient of this red curve at this point, i.e. the gradient of the black line. And we're looking for it in terms of x. We're looking for a formula for it, okay? So far so good. But also completely useless in terms of actually answering any questions so far. Dy by dx, the definition of the derivative, we've said it's called differentiation, this thing is called the derivative, it's also called the gradient function, of y. So if y equals f of x, the derivative is this thing. Limit as delta x tends to 0 of f of x plus delta x minus f of x over delta x. Fine, but how can we actually use that? Well, let's start with a function which isn't too nasty. Let's start with the function y equals x squared. And can we find dy by dx? So can we find the limit as delta x tends to 0 of, well, f of x plus delta x. So x plus delta x, well, f of x is x squared, right? So I'm going to take x plus delta x, I'm going to put that into the function x squared, so x plus delta x all squared. Take away f of x, so I'm going to put x into the function, it's going to spit out an x squared, there we go, divided by delta x. Okay, So let's have a look at this. This is a big mess of algebra. We've never seen this limit notation before. How the hell do we deal with this? Well, I don't know how we deal with this, but if we do, well, actually, I do know, and you will know in 10 minutes, but for the moment, we don't know how to deal with this. If we work it out, though, can you see it's going to be some sort of expression in x? So what it's going to tell us is, for the curve y equals x squared, it will give us an expression which we can use as a formula for finding the gradient. So I can say, when x equals 2, what's the value of this? And we can put 2 into this for x, and it will spit out a number, and that will be the gradient of the function x squared when the x coordinate equals 2. And you might be thinking, oh my goodness, right, we're going to have to use this formula, we're going to have to work out how these limits work. That sounds a bit complicated, but we're not, because already if we look at this, look, we can simplify this formula. Limit as delta x tends to 0. Well, x plus delta x all squared is x squared plus x times delta x plus x times delta x, so that's 2 lots of that. And I'm getting this from just doing x plus delta x times x plus delta x. Just expand it out as a double set of brackets, right? Plus delta x squared minus x squared over delta x. And then if we look at this, look, there's an x squared there and minus x squared there, so we can get rid of those. And we might still be thinking, oh my goodness, how am I going to deal with this limit thing? Well, okay, maybe we're going to have to deal with something, but look, I can factorize a delta x out of here and a delta x out of here. Remember, delta x is just one symbol, right? It's just a small amount of x, well, that's fine. So 2x plus delta x divided by delta x. And again, I don't know how this bit works, but look, that's just a number. It might be a small number, it's just a number, and this is just the same number, so I can divide the top and bottom of this fraction by that. So what have I got left? And I go, I'll worry about this bit later, but what I've got is 2x plus delta x. And now there's nothing I can do to simplify this expression in brackets, so I'm stuck here, right? Except limit of delta x tends to 0. Well, so if delta x is getting smaller and smaller and smaller, what's happening to this expression? Well, this is 2x plus a little bit, and then 2x plus a tiny bit, and then 2x plus a minuscule bit. So this expression here, if delta x is getting closer and closer to 0, this expression is getting closer and closer to 2x. Okay? Now, if you've never seen this before, what we've just said is this: y equals x squared, dy by dx equals 2x. This is the function, this is the derivative, this is the gradient function. If you've never seen this before and you're not excited by this yet, well, either you're never going to enjoy differentiation or maths, or you've not quite understood it yet. Think about what this does for us. If I want to know the gradient of y equals x squared, previously I would have to get a graph, draw a table of values, draw my function as carefully as I could, and you'd say, okay, at the x coordinate 4, and okay, x coordinate 4, so I'd go up to the graph and I'd put a point there and I'd draw a tangent and I'd measure the y change and the x change, and I'd do it as carefully as I could, and I'd come up with a number, and I'd still wouldn't know how accurate it is. But now I've got a gradient function, I've got a derivative. This expression is the expression that I can use to find the gradient of this function. So if you say to me, right, I want to know the gradient of this function when x equals 4, I go, x equals 4, brilliant, just take your x coordinate and stick it into this expression here. So the gradient of this function when x equals 4 is 8. That's simple. The gradient of this function when x equals 7 is 14. Okay, I don't have to draw the function, I don't have to draw the curve, I don't have to worry about how accurate it is. It's exactly accurate. The gradient of the function y equals x squared at the point where x equals 4 is 2 lots of 4, which is 8. Okay, so you might be thinking, well, hopefully you're thinking, well, that's pretty good. That's going to save us a lot of work if we ever need to know about gradients of y equals x squared. But it's still not that exciting, because most functions we deal with aren't y equals x squared, right? We've got hundreds of functions, infinitely many functions, actually. How can we deal with other functions? Well, firstly, this thing is how we find the gradient function. We don't have to go back to this thing every time we need a gradient function. What we do is we work out families of functions or particular kinds of functions, and then we remember the derivative. Okay, so if you ever need the derivative of y equals x squared, you know it's 2x. For the first year of A-level, the only functions that we need to deal with are functions which are powers of x, okay, and combinations of functions which are powers of x and things like that. So we're not going to worry about differentiating things like sine and cos and tan, and if you know about them at this point when you're studying this chapter, I don't know, but things like e to the x and natural log of x and things like something to the power of x. We're not going to worry about any other fancy functions, just x to the power of something. That's what we're going to worry about. So let's think about that. Y equals x to the power of a, and if you think about it, if we can deal with this, maybe that's enough to deal with things, and we will find out that it will be enough to deal with things like x to the power of 3 plus x to the power of 2, and if I throw in a constant in front of that, then that's not going to make too much of a difference. We're going to be able to deal with those things as well. If we can do this one, that's the tricky bit. So this function is made up of x to the power of something, x to the power of something else, and this x to the power of something is times by a constant number, but that's going to be okay as well, we'll find. So basically anything that looks like this, quadratics and similar kinds of functions, we're even going to be able to deal with things like x equals square root of x, because, y equals square root of x, because that is x to the power of a half, so it's still x to the power of a number, so that fits in this family of functions. So if we can do this, we will find we've got lots of derivatives that we can play with. How do we do this? Well, the gradient function, the gradient of this function at the coordinate x is given by the limit as delta x tends to 0 of f of x plus delta x, well that is x plus delta x to the power of a, minus f of x, well that is x to the power of a, divided by delta x. What happens here? Well, this is where you need to have done the binomial expansion chapter, and we need the binomial expansion of this bit here. If you don't know binomial expansions, you might just need to fast forward, get the result at the end of this derivation, and trust me on it. But you will need to come back and learn it at some point, because these days you need to know it on the exam. So x to the power of a plus a lots of x delta x, and the delta x is going to be a power 1, so the x is going to be a minus 1, plus a squared, sorry, not plus a squared, plus delta x squared, x to the power of a minus 2, times a constant, and that constant is called a choose 2 or a 2 in brackets, but it's times a number, plus delta x cubed, x to the power of a minus 3 times some other constant, a choose 3, and so on until we end up with delta x to the power of a. That's the expansion of this bit, binomial expansion. Take away a squared, x to the power of a, there we go, all divided by delta x, and you might have spotted there's an x to the power of a at the start, there's an x to the power of a at the end, so that and that, we can get rid of them. And you also might have spotted, similar to the x squared example, there's a delta x here, 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 so I can factorise out the delta x's, and I've got a x to the a minus 1 plus something times a x to the a minus 2 delta x plus something else times x to the a minus 3 delta x squared plus, and so on, up to delta x to the now n minus 1. All of that lot divided by delta x, this delta x cancel out, and what have we got? Limit as delta x tends to 0 of this thing, a x to the a minus 1. And then, now, I'm getting a bit bored writing all this stuff out. Can you see there's a delta x here? There's a delta x squared here, there's a delta x. So I can say this is delta x times by that, times by that, times by some stuff, plus this stuff times delta x, so some more stuff, but this time with the delta x in it, plus some more stuff times the delta x squared. Now, I don't expect you to write it this way in the exam, but the important thing is that there's a delta x times some stuff, okay? Now, what if delta x is getting smaller? Well, if delta x is getting smaller, this is something very, very small times some stuff. And your first response to that will hopefully be, well, something very, very small times some stuff should be something very, very small. And if this delta x gets small enough, then this thing will be more or less equal to 0 and would just vanish entirely and just leave us with this bit left here. And then maybe second thoughts, you think to yourself, well, hang on a minute though, something very, very small times a number should be something very, very small, right? Except what if that number is very, very big? Well, let's have a look at this number. What's it made up of? Well, actually, it's made up of x to the power of something, so that could be huge, couldn't it, right? And a choose 2, a choose 3, so if a is a very big number, maybe these are big numbers here, except that delta x, remember, is getting closer to 0. It's getting as close to 0 as we want it. It's getting closer and closer and closer. So let's say this number here, when we calculate it all, inside this bracket, let's say it's 1,000,000. We'll take delta x to be 1 divided by 1,000,000,000, and suddenly this whole thing is small. And now take delta x to be 1 divided by 1,000,000 trillion, or a 1 followed by a page full of zeros, and this whole thing is very, very small. So, okay, fine. Well, what if this thing in the brackets turns out to be even bigger than 1,000,000? What if it turns out to be 1,000,000,000,000? Well, just take delta x to be 1 divided by lots and lots and lots of this number, right? You can make delta x as small as you want. So the clever thing about this delta x tends to 0 bit is that delta x can get smaller and smaller and smaller. However big this number is, this delta x can be smaller, disproportionately smaller than however big this one is. In other words, delta x can get small enough that this term here, this whole bit, will vanish. So what we're left with, ax to the a minus 1. Okay, so what have we got then? We've got, if y equals x to the power of a, dy by dx equals ax to the a minus 1. So let's say y equals x cubed. Well, the derivative, dy by dx, equals 3x squared. What if y equals x to the power of 7? The derivative equals 7x to the power of 6. You just take the power, take 1 off it, put the old power in front, and times by it. It's that simple. If you wanted to know the gradient of the function y equals x to the power of 7 at the x coordinate 2, then you do 2 to the power of 6 times 7, that will tell you the gradient. If you wanted to know the gradient of the function y equals x to the power of 7 when x is 10, it's 10 to the power of 6 times 7. So 7 million is the gradient when x equals 10. Okay, pretty big gradient. But the point is, we've got an algebraic way of doing it. We've got an algebraic way of finding these functions here, and those are the functions which will tell us the gradients of these functions here. Okay? So that's everything we need to know from section 12.1 and 12.2. Quite a bit of detail. Hopefully that will make sense and that will help. Now, these things that I've scribbled out in the top corner of my page, when we get to section 12.3 of this chapter, we find out about how to practically do differentiation, and I will start that in another video.